Welcome, everybody. So for the last week or so, we've been talking about the electric potential and the electric potential difference, or voltage, which is why we use the capital V for it. And we haven't talked too much about representing V. One thing that is especially tricky about representing V is that it's a function of space. It depends on where you are, left, right, up, down, forward, back. And we've drawn a few electric potential energy diagrams, things where we're just kind of drawing a one-dimensional graph, but that doesn't really capture the full depth of the electric potential. So we're going to talk today about representing V in a different way. And that different way, as you saw in your Get Ready question, is something called an equipotential diagram. I have an example of an equipotential diagram here. This, in fact, is the equipotential diagram that you would draw for a point charge. You can imagine putting a little point charge, we'll make it red, here at the very center of the diagram, something like that. So there's a little point charge there, and then what we've drawn here is an equipotential diagram. Now, an equipotential diagram shows a lot of information in a compact way. It's a two-dimensional representation. You can actually make it three-dimensional if you're willing to draw spheres and things like that. But it's a two-dimensional representation. And the way it works is each of the lines that you see represents the region of space where the potential is constant. That's why it's called equipotential, because the potential is equal along each of the lines. In a kind of proper version of this diagram, you would want to give a number to each of the lines. So for example, you might say that this number were 10 volts, the kind of innermost one, and that this one were 9, and then 8, and then 7, 6, and so on and so forth. And when you do that, you are almost always going to be really careful to make sure that the difference in voltage between the lines that are closest to each other is the same. You wouldn't go 10, 9, 8, 5, right? You wouldn't skip a number in there. You want to make sure that they're spaced out evenly in terms of the value of the electric potential. It doesn't mean it has to be separated by 1 volt. You could easily do 10, 9.5, 9, 8.58, and so on, or 10, 8, 6, 4. Any of those distributions would work as long as they're evenly spaced. And the value of that is that because they're equally spaced in voltage, but they are not equally spaced in distance, we can kind of read what this map looks like by looking at how close the lines are together. There are other similar representations to this one. If you've ever worked with a contour map, either because you went hiking or you did surveying or skiing, all of those would use contour maps like this one, where the lines are representing height. Here the lines aren't representing height, they're representing the value of the potential. But we can still think profitably about it as something analogous to height. Let's see. Do I want to say anything else about the equipotential map here? I think I'm going to let that stand, and I will pitch you back over to Top Hat to think a little bit more about how potential works.